So now let's go into the real details about the actual system of CloudClustering. So here's the serial k-means algorithm that we just saw. It's a conventional, very widely used in study. So it only runs on one machine, and so it's going to be slow for large data sets. So for example, with big news, we need more we need parallelization to take care of this large input. So here you can see we start, we initialize, we assign points to centroids, we recalculate, and we keep looping. So here's how to parallelize k-means so that it can run on multiple machines. So we split up the points into partitions that give one partition to each worker. Then the workers do their processing. They assign the points to centroids, return some partial sums, which the server can aggregate back and recalculate the centroids based on those. So here you see that like the red or orange color runs on the server, and then the blue colored steps run on workers that all run in parallel. And so the main difference, which I mentioned, oh sorry, this should be blue, just so you know. The main difference that I mentioned is that the centroids are recalculated using partial sums rather than by looping over the entire data. The reason for that is that if the server went into each cluster and calculated the mean of that cluster to figure out its new centroid, then things would be very slow because the server is taking O(n) time to go through all those points. So here we have each worker calculate its own partial sums and let the server merge that all together. So here's how CloudClustering actually implements this parallel algorithm on Azure. So I'll just walk you through how each step of the algorithm maps to this Azure diagram. Sure.
So the worker gets one centroid with all its points, or you partition by points?
That's a great question. So actually, partitioning happens. It's completely arbitrary. So partitioning is just in this case it's just based on where the points are in the overall blob. But basically, it's the goal is that we partition evenly. The centroids don't come into this, so the clusters aren't relevant. And so the way that works is that workers sort of treat their partition as if it were the entire data set, and then just calculate the partial point sums and return them to the server, which merges them all back together. So here's the diagram. So there's a server. There's one queue for each worker, which the server enqueues tasks and lets the worker process them. There are two blobs. There's a points blob and centroids blob, and so one important point is that the points blob stores not only the coordinates of each point, but also the ID of the closest centroid. So the reason for that is that is to support that stopping condition that I mentioned earlier, so that each worker can compare the old value of this closest centroid ID and the new value, and see if they're different. If so, then we had 1 point changed. So this lets us aggregate the total number of points changed and say, is it greater than 0? If so, stop, otherwise not.
Does the algorithm work entirely in memory, or does it sort of each worker works in memory on its set of points, or does it go back to the blob each time and update it?
So this is actually I did some work on this, but which is data affinity and caching. So the overall thing. So here's the simple explanation, which is that workers just act as stream processors by pulling in the network data from the blob and processing it and writing it back out. So there's memory and disk don't come in initially, but it's a great optimization that we do apply. All right, so here's the quick overview. So in the initialization step, the server instance creates those two blobs, and one contains the points that the user gave, and one contains a random set of centroids. So next, in the split points into partition step, it's right there, the partition work step. The server uses queue messages to deliver partitions of this points blob to the workers. As I mentioned, those partitions are arbitrary. So there's chunks that workers work on as if they were the entire problem. So next, in the assign points to centroid step, each worker does this assigning calculation on its own partition of points. And it reads from the central points blob and writes the results back to the point blob. And it's writing those updated centroid IDs that are here in this tuple x, y closest centroid ID. It's updating those centroid IDs. So next, each worker calculates those partial sums. So the partial sums are actually based on each worker takes a partial sum for each cluster within its partition. And essentially it's treating, as I said, this partition as if it were the entire problem. And so it calculates the partial sums, and then it sends those back to the server by putting the result on this task result queue. And the server is able to aggregate across workers for it to sum up and average those partial point sums for each cluster to recalculate those centroids. That's in this step. And then the server, of course, writes the new centroids to the centroids blob, and the cycle continues. So we partition work, keep going. Okay. Next,
So
I'd
the
like to go.
workers never read actually from the centroid blob at all.
The worker, actually, they do. I didn't put an error there, but they do for the assigned points of centroid step. The workers need to read from those central list of centroids and figure out for each point what's the closest center. Okay, so
I have a question about previous one. So you don't need to keep track of these assigned centroids if you create the stop condition, like calculate the difference between the
yes,
centroids.
right. So that would be a great optimization, which is a modification to the actual algorithm, which I'll go into in the future work.
But we are not sure it's correct.
Yeah.
Exact same as this converge condition.
Yeah, I
It
know.
may be different.
1 point change is like a so.
Yeah, I know that.
You don't
Yeah.
stop.
Yeah, so
But this is
currently here-
traditional.
That's-
Yeah.
Um,
Yeah, so
If
currently
in
we're
two iterations
we're-
that didn't change at all, it means no point change.
Yeah, but we need to prove that if like the traditional algorithm is no point change.
What I'm saying is, if you change
No.
epsilon, you don't know, you cannot stop it. If it didn't change
at all.
zero
Yeah,
two
zero,
times,
yeah, two
That's
times,
just
yeah.
converged.
you can stop, right?
Well, sort of, except that it's still possible for that to happen. I mean, in theory, it's unlikely. But